Welcome to the presentation More Models of Walks Avoiding a Quadrant, which is joint work with Mireille Bousquet-Mélou. First of all, I would like to thank the organizers for making it possible to give this talk online despite the complicated times. In this talk, we're going to address the problem of how many walks of length n, starting from the origin, avoid the quadrant. So here you see an example of such a walk. For such a walk, we fix the starting point, which should be the origin. Then we fix a certain subset, which is a subset of the 8 possible nearest neighbor jumps, which are also called small steps. And then we fix the 3-quadrant cone, which consists of all possible values in the plane, x and y coordinates, which do not have a negative x and a negative y coordinate. And then we're interested in the number of this walk. Note that this is an example of a non-convex cone, and in 2-dimension 2, all non-convex cones are basically the union of 2 half spaces, and after a linear transformation, they are equivalent to such a model. So in this talk, we're going to focus on the steps where we allow on the model where we allow all possible step sets. This model has, for example, applications when you have a broken chessboard and you want to determine how many moves a king can make on this chessboard. That's why we'll call this model the king walks. More seriously, this is a model for many discrete objects, for example, in combinatorics, probability theory, statistical physics, or queuing theory. In there, many problems are modeled by lattice path problems, and in there often space constraints like non-convex cones appear. So how many interesting models are there in the 3-quadrant cone? For the small steps, there are a priori 256 different models. However, some of them are equivalent to models, for example, in the full space or the half space. So these 2 models here are equivalent to the full space models because the space constraint doesn't change anything for them. And for this model here, only one of the boundaries is important. So we know that these cases are either for these full space models rational generating functions or have algebraic generating functions. Moreover, some of these models are equivalent to other models in the collection due to symmetry, like a diagonal symmetry, like for this case. Then we are left with 74 interesting models. As a side remark, in the quarter plane, which I'll define afterwards, there are 79 different non-trivial models. So here you see the 74 different interesting models in the 3-quadrant cone. The king is shown down here. Later on, I will come back to this slide and show you what is already known on these models. So what are interesting questions? Let me be more precise. What we're interested in is, as I said, for example, the total number of walks, which I denote by Cn. This is the number of walks of length n. Then we're interested in closed forms or asymptotics. Moreover, the same question might be asked for the walks ending at a certain point x coordinate I and y coordinate j. They are denoted byCijn. Then we encode these 2 sequences into generating functions. By Ct, I denote the generating functions for the total number of walks of length n, and in Cxyt, we denote the generating function where we encode the walks ending at x coordinate I and y coordinate j after n steps. Then we're interested in if we are able to express these generating functions as get closed forms or functional equations. And moreover, we're interested in their nature, meaning are they rational, algebraic, definite, or not definite. So let me define this terminology. A formal power series Ct is rational if it can be written as a fraction of 2 polynomials. It's algebraic over a ground field, here Qt, if it satisfies a non-trivial polynomial equation. We call it definite if it satisfies a non-trivial linear differential equation with polynomial coefficients. Here you see the generic form of such an equation. So why is it interesting or important to be definite? Well, definite functions have very nice and effective closure properties like sum, product, differentiation, or substitution of algebraic functions. Furthermore, we have fast algorithms to compute coefficients and to also get asymptotics. And these effective tools are the reason why definite functions are very interesting for us. So let me tell you what we know about the solved cases, what we know about the cases in the three-quadrant cone so far. So let me start here with the cases where the full trivariate generating function in x, y, t is definite. We call it definite in these three variables if it's definite in each variable, meaning that it satisfies a linear differential equation with polynomial coefficients in each of its variables. The first two cases of the simple walks and the diagonal walks were solved by Mireille Bousquet-Mélou in the first paper on this topic, starting the research in this direction. Later on, Rachel and Trottignon solved these additional three cases. And in this talk, I'll show you that the king is also definite, that the king walks also satisfy, fall into this class. Furthermore, we have some partial results. So for some of these classes, it has been shown that the generating function of excursions, which is the generating function shown here of the number of walks ending at the origin again after n steps, is definite as well. Note that if the full differential generating function is definite, then by closure properties, also the generating function of excursions is definite. Therefore, these four cases give strong hope that the full generating function is also definite. Moreover, we know already of 51 cases which are non-definite. Let me come back to the picture and show you the taxonomy we know so far. In red, you see the non-definite cases. In yellow, there is the cases where the excursions generating function is definite. And in green, we see the cases which are indeed definite. Note that the dark green cases are actually not only definite, but also algebraic. Every rational function is indeed algebraic, and every algebraic function is also definite, meaning that this makes it a more precise taxonomy. So let me now introduce a very important concept, which is very classical and played an important role also in the solution in the quarter plane. So from now on, I denote by x bar the 1 over x and by y bar 1 over x to simplify notation. Then I define the step polynomial as this polynomial here, which encodes all possible steps here for the king. So x denotes the jump to the right, and y denotes the jump up, so in the x direction and in the y direction. And then the others are analogous. For example, x bar, y bar denotes the jump southwest. Then the important observation here is that s of x is left unchanged by some rational transformations, which are shown here. So x is changed into x bar and y is changed into y bar. These are actually involutions, and they generate a finite dihedral group G. Note that this group can be defined for any model with small steps analogously. Now in the quarter plane, this group was very important. The quarter plane is the convex cone, which consists of all points in the Cartesian plane which have non-negative x and y coordinate. So here you see an example of a simple walk in the quarter plane. Then we analogously define the generating function q of x, y, t of walks starting at 0, 0 and ending at I, j after n steps. The striking result here in this domain is the following, which was the joint effort of many, many contributors, where I just list a minimal set here. So it says that the series Q is definite if and only if this previously defined group is finite. So this basically connects an analytic result with an algebraic one. Now in this talk, I'll show you that similar things happen for the king. And basically, I show you here a certain algebraicity phenomenon which connects the quarter plane with the three-quarter plane. So I abbreviate C of x, y, the generating function in the three-quarter plane for the king starting from 0, 0. Then C decomposes into a formal power series A and a linear transformation of the generating function of the quarter plane walk for the king. And then A is algebraic of degree 216. This then basically shows that C of x is definite by closure properties because Q is definite. Moreover, we know about this function A that it satisfies the following functional equation, which looks very similar to the lattice path generating function, to the lattice path interpretation, I'll come back to that later, of walks. And A minus and A0 are actually algebraic of degree 72 and 24. Note that such a phenomenon was already proved as well by Mireille Bousquet-Mélou for the simple walk and the diagonal walk. And we will follow these steps, and we extend this approach by guess and check approach, and we add nice, neat algebraic extensions, which will be necessary in order to understand what's happening here. From this result, we can get asymptotics, for example, of the number of excursions or the total number of walks. And what I want to pinpoint here is that with our approach and with our result, we're able to make the multiplicative constant, which was unknown so far, completely explicit. This then refines previous results of Denisov and Wachtel and Mustafa by this precise multiplicative constant. And if you want to do so, we're also able to compute low-order terms very easily. So let me dive now into the proof. Everything starts with a step-by-step construction which models these walks. So a walk of length n plus 1 is constructed from a walk of n in such a way that we append an allowed step. This corresponds to multiplying with the step polynomial and t, which corresponds to another jump. A walk is before of that also allowed to be, of course, empty. That's how everything starts. But then, if we add more jumps, then at some points, there are some jumps which are not allowed. For example, on the negative y-axis, we are not allowed to jump to the left. On the negative x-axis, we are not allowed to jump down. And if we are at the origin, we're not allowed to jump south-west. This corresponds to these three parts. C minus y bar denotes the generating function of walks ending on the negative y-axis. And by the symmetry of the model of the king walks, this corresponds as well to walks ending on the negative x-axis. In C0, I denote the generating function of walks ending at the origin. So then this gives the first important observation that we have the following kernel equation for the generating function of walks avoiding a quadrant, whereby blue in K I denote the so-called kernel, which is nothing else than 1 minus t s of x, y. Now the first important observation here is that this kernel equation looks very, very similar to the kernel equation for quadrant walks for the king. So here you see the kernel equation for the quadrant walks. And in color, I map corresponding constructions. So what we can do now, and what was very crucial was what I mentioned before, was the group in the quadrant case. And from this group, we're able to define the so-called orbit sum. The orbit sum is not that important what it looks precisely. I've shown it here. But the important thing is that it is exactly the same for these two models, and it gives exactly the same result on the right-hand side. A rational function which is completely explicit. K is again the kernel, which I've shown you before. What we observe as well is that this orbit sum is also satisfied by three additional functions which depend on Q. Basically, what it means that you replace Q of xy by one of these functions and put it on the left-hand side. And then we get exactly the same right-hand side. So what we can do now, and what is our idea, is to create a zero orbit sum. Why do we want to do that? Because in the quadruplane, models which had a zero orbit sum actually had an algebraic generating function. And that's what we're aiming at. So here I just recall the same lines from before. And what we do, we introduce a of x as this function here. And then we get, by construction, that the orbit sum is 0. And moreover, we get the functional equation I've shown you on the previous slide. Now, this is actually, now after we have performed the step-by-step construction, can be interpreted as a lattice path generating function with starting point 0, 0, minus 2, 0, and 0, 2 with certain weights. So what we want to do now, we want to analyze this functional equation. If we know A, we will characterize C. The next step would be now to use this kernel equation, this factorization on the left-hand side, and cancel the kernel by substituting certain functions in here. But this is not allowed because a of xy still contains negative powers of x and y. Hence, as the next step, we split a of x into 3 different parts shown here, into p of x, which corresponds to the positive or actually non-negative part of the cone, and into mixed terms here. By symmetry, this is the same function m for both of these. And then p and m are actually power series, meaning that they have non-negative powers of x and y. Then we get, after some work, the connection between p and m, which is shown here, and after some more work, basically a functional equation for m of x, which only contains m, no p, and m and certain specializations of m. It's not important how it looks like precisely, but we still have this factorization with the kernel on the left-hand side. So now, as we have power series, as m is a power series, we're allowed to cancel the kernel, cancel the left-hand side, and after more work, we arrive at a functional equation for m0x with one catalytic variable, namely x only. This I'd only show here as a polynomial equation in m0x with 4 half-known series. I write here b1, b2, b3, b4. They say they are half-known. They only depend on t, not on x, but they still depend on our unknown m. So this big polynomial equation is in theory solvable with the theory from Mireille, Bousquet-Mélou, and Hahn. But unfortunately, the polynomial equation was too big for our computers. So how we continued, we used the guess and check approach to get equations for these BIs. So what we were able to do from the first 2000 terms of the linear recurrence for Cij, we were able to guess algebraic equations for the BIs, algebraic equation of degree 12 for B1 and of degree 24 for B2. Then with these algebraic equations, we needed to come back and prove that they're actually our algebraic equation from the previous, from this polynomial equation here. In order to do so, in order to simplify things, in order to be able to deal with it, we investigated their algebraic relations. The algebraic relations are here, my last technical slide. And on this one, I show here on the right the tower of algebraic extensions which are needed to understand the BIs. Note that the striking result is that all of them live in the same algebraic extension. So basically the ground field Qt, we adjoin an element U, which is of degree 4. And here it is completely explicit. And here we spend most of our time to find nice relations and nice primitive elements which we can work with. Then we continued. We get an element V, which is of degree 3 over QTU, and an element W, shown here, which is of degree 2 over QTV. Then we get that B1 is actually in QTV, and B2, 3, and 4 are in QTW. Then with these simple relations, we were able to prove that these BIs, the guessed ones, are actually the correct ones, and solve for a final result. So here what we get, for example, is that B4, which is nothing else than M00, and which is also nothing else than the walks in the 3-quadrant cone ending at -2, 0 satisfies this nice closed form. And this then, with this result, we come back to our main result. The precise knowledge of V and W allows us to prove everything, as I said, and we get that the generating function of a king walk restricted to the 3-quadrant cone satisfies this nice decomposition into an algebraic and definite functional equations, where the algebraic generating function is actually algebraic of degree 216 and completely explicit. Next steps is then to go on. So for now, our approach is applicable to the following 7 models, and we are able to define A of x with orbit sum 0. The first 3 are now solved, and for the last 3, we were able to guess algebraic equations for the generating function a -1, 0, meaning the generating function of the respective a ending at -1, 0 or at -2, 0 if it didn't exist. And this gives strong hope that we are able to solve these problems as well. So thank you very much for your attention, and thank you for your interest in this talk.